This video builds on a skill we learned in grade 11 on solving radical equations. And now we take it a step and talk about radical equations graphically. So just as a reminder, you have to remember that radical equations will have this radical sign somewhere in them. They will also have an equal sign, which lets us know that it's an equation. So an example of a radical equation is something like this. The root of x minus 3 minus 3 equals 0. And again, we did learn how to do this back in grade 11. And this equal sign is the difference between a radical equation and a radical expression. So when there's an equal sign, we're trying to figure out what x equals. So let's just review the steps for actually algebraically solving these radical equations. The first step is to actually isolate the radical stuff. Lack of a better word, we're just using stuff. So that means anything that's under the radical sign, try to get it on one side of the equal sign. Then what we try to do is we solve for x. The last thing that we do is verify that our solutions actually work in the original equation, and we can then reject any extraneous roots. Now this is not an option when we're solving radical equations, because we could see that some extraneous roots have to be rejected, and if you don't do that, you start to think that there's actually more answers to the question than there actually is. So for radical equations, we have to always verify to make sure that our solutions are indeed correct. So let's look at this example. We're going to solve the square root of x minus 3 equals 0. And we're going to first solve it by reviewing how we did this algebraically back in grade 11. So we'll just rewrite this. The root of x minus 3 equals 0. Now the first step that we did say was we want to actually try to isolate this root of x minus 3. So how do we do that? We simply add 3 to both sides. So if we add 3 to both sides, we just are left with the square root of x minus 3 equals 3. And then we did remember last year as well, to get rid of that radical sign, we simply have to square it. But what we do to one side, we have to also do to the other. So we have to square 3 as well, which is 9. And then if we square a radical, we're actually just left with the radicand, so x minus 3. Now this turns into a simple solving question from back in early junior high. Just add 3 to both sides, and a possible solution may be x equals 12. But now we actually have to go through, and we do have to verify this answer to make sure that it's not an extraneous root. So we go back to the original equation, the root of x minus 3 equals 0. And we want to try to see if the left side will actually equal 0 when we put in the 12 for the x. So 12 minus 3, take the root, subtract 3 equals 0. And some of us can start to see that the root of 9 minus 3, we're trying to prove that equals 0. So 3 minus 3 is indeed 0, which does tell us that 12 is a solution to this question. And we can now show this graphically on our calculator. So we put in the left side of the equal sign into y1, the right side into y2, which is 0. And what we go on to do next is we want to graph this, and we're going to graph it with a suitable window so we can actually see what's going on. So if you look, our solution we already know is 12, so we're going to have to adjust our window accordingly. So we make more x's on the 12, and now we can see the graph of the radical, and the graph of y equals 0, we really can't see because it's sitting right on my x-axis. So if we take a look, there's y equals 0, and we're actually trying to figure out where these two graphs intersect. So to do that, we just go to second function, trace, and under there we go to option 5, which is the intersection. and we just say, you know what, I want to find that first curve with the second curve. Let it find our answer for us. And when you hit enter, you see indeed the solution is x equals 12. So graphically, we can also see that the solution to this is 12. So let's look at a similar example now. We got the root of x minus 3 plus 3 equals 0. We're going to solve it algebraically. We'll start by rewriting the equation to start our work. We want to isolate the radical stuff, the x minus 3. So we're going to take a 3 away from both sides. And we can see the root of x minus 3 should now equal negative 3. Some of us start to see a little red flag going up right now, but if you don't, we just continue with our solution. As we did last time, we simply square both sides to get rid of that radical. So we're going to square the root of negative 3, which still provides me with a 9. And then squaring that, we're left with just the radicand. We go back, we add the 3 to both sides, and we're left again with x equals 12. Now we want to verify to make sure that this is a possible solution to this equation. So when we verify, we always start our verification right back in the original equation. So we rewrite it and try to make the left side of the equal sign equal the right side of the equal sign. So we put in the 12 again. The root of 12 minus 3 plus 3 equals 0. And we're getting the root of 9 plus 3 equals 0. And it should be clear now that 3 plus 3 is not 0. Therefore, x cannot equal 12. And this is what we call an extraneous root, which means, or an extraneous solution, which means our solution itself algebraically held sense. We did all of our work right, but when we verified it, it just didn't work out. So the answer to this question is simply, there is no solution. So we're going to examine this again graphically in a minute. To show that indeed when we look at these, how this would look if there's no solution, what we'd actually see. So we have our two equations in y1 and y2 on the equal sign. And we're going to go right back to where we did it before. We could either, because this is equal to 0, we can either find a 0 or a x-intercept, or we could say, here's the radical, here's the line y equals 0. They're not intersecting. Therefore, there is no solution. So graphically, we can also see that since there's no intersection point, there is no solution to this problem. So we're going to move on to a little bit more complex equation now. And in this complex equation, we have the root of 2x plus 7 minus x equals negative 4. So we're going to start by isolating that radical again. Rewrite the original question to show our work. To isolate the radical, we're going to add x to both sides. So now on the left-hand side, we simply have the root of 2x plus 7, and this should equal x minus 4. So now nothing changes. We still want to get rid of that radical, so we want to square the left side and the right side. But now, when we square the right side, we can see we're actually squaring a binomial. So the left side, we're left with the radicand, but on the right side, squaring a binomial, we're left with x minus 4 multiplied by x minus 4. So what we have to do is FOIL that right side out. And if you FOIL it out and simplify, we get x squared minus 8x plus 16. And this is still all equaling the left side, which is 2x plus 7. So now we have a quadratic situation where we actually want to go through and get everything on the same side of the equal side and make it equal to 0. So you want to push it over to where your x squared term is positive. So in this case, it's the right-hand side. So we're going to take away the 2x and take away the 7 from both sides. So when we do it, we're left with 0 on the left-hand side. And on the right-hand side, we're left with the quadratic that is x squared minus 10x plus a 9. So now, from our quadratic unit in grade 11, we should be able to remember that now to solve this, we want to factor this trinomial. And when we factor it, we'd set the factors equal to 0 and solve for x. So x squared minus 10x plus 9 factors to x minus 9 and x minus 1, which leads us to the solutions of x equals 9 and x equals 1. Now these are possible solutions, so we want to make sure that we could verify that these are not extraneous. They both could be answers. One might only be an answer, or there could be no solution to this problem. So to verify, we go back to our original equation of the root of 2x plus 7 minus x equals negative 4, and we verify both of these individually. So the first one we're going to verify is x equals 9 and see if this works. So we substitute a 9 in for the x in both places. We want to see if that would equal negative 4. So when we go through the work, we have 2 times 9 is 18 plus 7. Well, that's the root of 25. Minus 9 equals negative 4. Now you can see that 5 minus 9 does indeed equal negative 4. So x equals 9 is a solution to this radical equation. Now let's verify that x equals 1 is either a solution or verify that it's an extraneous root in the situation. So we plug it in for both of the x's again. So 2 times 1 plus 7, all under a root sign, minus 1 equals negative 4. We simplify the radicand in this radical, and we get 2 plus 7 is 9, minus 1, minus 1, I should change that, I made a mistake there. We got 3 minus 1 equals negative 4. And we could see that 3 minus 1 definitely does not equal negative 4. So x equals 1 is what we deem an extraneous root. So it's not a solution to this situation. And again, we can go through and prove this graphically on our calculator. Left side and right side into y1 and y2. We find suitable window settings so that we could see any intersection points. And now we can see the two graphs. We have the radical, and right there is the intersection point. We can go through and solve that the same way by finding the intersection, second trace, number 5. Went a little too far there. I have to go back to second trace, number 5. Find the intersection of the first curve, the second curve. Let it find the answer. And we can see x equals 9 is an answer. We proved it graphically. And if we just try to examine x equals 1, we could see those two graphs aren't intersecting there. So we could see on the graph as well that that's an extraneous root. So we'll finish this lesson with doing a radical equation straight graphically, no more algebra, and we'll show how we can get the answer as well. So we're going to solve x plus 3 equals the root of 12 minus 2x squared graphically. We're going to sketch it with appropriate window settings and find our answers. So in your calculator, you put the left side into y1, put the right side into y2, we go back to our standard window, which is zoom 6, and we could see that, okay, here is our graph. And we can see that there are two intersection points. So let's go and try to find out what they are in our calculator. So we just go back to second trace and we find the intersection of these two graphs again. So let's go first curve, enter, second curve, enter, and let it find the answer. And one of them, we'll say we'll round to 3 decimal places. One of the intersection points is when x equals 0.414. So we'll record this finding, x equals 0.414. And now we have to go back and try to find that other intersection point. And to do that, it's just a little bit of a skill that you have to know. We have to now move our cursor. We go back to second trace number 5, the intersection, but move your cursor closer to the other intersection point so it knows it wants to find that one. So there, I'm really close to that intersection. Now you just let it go first curve, enter, second curve, enter, let it find the answer. And again, we'll round to 3 decimal places, and we see the other answer is x equals negative 2.414. We could verify it to make sure that both the left side and the right side equal each other, but we know from our graph that we could see that those are indeed intersection points. So the verification here to find an extraneous root is not needed because we can see that they are actually intersection points and neither answer is extraneous. So we just trace the graph, and now it's just a matter of writing down properly our window settings. And our window settings, and this is on our formula sheet, all we do is say our x, it was our standard window, so x min was negative 10, x max was 10, and the x scale is 1. And the same thing with the y min is negative 10, and then 10 and 1. So that's how we can solve algebraically and graphically radical equations.